Introduction. Mathematics has a language of its own. It is formed on a strong foundation of the theory of sets and propositions. George Cantor is considered as the inventor of set theory. A set is intuitively defined as a collection of objects called elements. Usually, sets are given names by uppercase letters and its elements by lowercase letters. To write that A belongs to A belongs to A, the notation A belongs to A is used, and of course A does not belong to A represents that A is not an element of A. The notion of a set is very simple. Still, a deep thought is necessary for one to properly understand it. To some authors, a set is a well-defined collection of objects. By the term well-defined, they mean the quality by which one can judge whether a given element is a member of the set or not. In this regard, in 1901, Sir Bertrand Russell posed a question. He considered a set with its elements as all possible sets. The question was whether the set itself be a member of it. Neither yes nor no could prove to be an answer. This made people realize that a hard and fast definition is not essential to discuss sets. Russell's question is now known as Russell's paradox. Symbolically, it is stated as follows. Let R equals set of all x such that x is not an element of x. Then R belongs to R implies in both ways that R is not an element of R. There are two ways of representing a set. They are the enumeration or roster method and the rule or set builder method. In the roster method, the elements are written within brace brackets separated by comma. For example, A equals set A, B, C, D represents a set consisting of 4 elements. In the set builder method, the rule by which the elements of the set are obtained will be described. A set S may be written in the rule method in the form S equals set of all x such that x satisfies a suitable condition. The set A equals set A, B, C, D can be represented in the rule method as A equals set of all x such that x is one of the first 4 letters of English alphabets. Usually, roster method will be convenient to represent a set with few elements and the rule method to represent a set with a large number of elements. Sets can be diagrammatically represented using simple closed figures like rectangles, circles, ellipses, etc. They are called Venn diagrams. There are different types of sets. First is empty or null set, a set having no elements in it. It is denoted by a brace bracket having no elements in it or using the symbol phi. There is an extreme opposite concept also, namely the universal set. It contains all elements of any set we consider. It is usually denoted by U. Next is subsets and supersets. Let A and B be 2 sets. We say that A is a subset of B denoted by A subset of B if every element of A is an element of B. In this case, B is called a superset of A. Equality of sets. 2 sets are equal if both A subset of B and B subset of A. Next is finite set. It is a set having finitely many elements in it. The number of elements in a set is usually called the cardinality. We denote the cardinality of the set A by #A. Next is infinite set. If a set is not a finite, it is an infinite set. In mathematics, the following are certain commonly used sets of numbers. n equals set 1, 2, 3, etc., the set of natural numbers. W equals set 0, 1, 2, 3, etc., the set of whole numbers. Z equals set 0, 1, 2, 3, etc., negative 1, negative 2, negative 3, etc., the set of integers. Q equals set of all p by q such that p and q belongs to set and q not equal to 0, the set of rational numbers. R, the set of real numbers which can be marked on the number line. C equals set of all a plus ib such that ab belongs to R, where I square equals negative 1, the set of complex numbers. All these sets of numbers are infinite sets. Using given sets, new sets can be formed by basic set operations. First is union of two sets. For the sets A and B, the union A union B is the set of all elements belonging to either A or B. That is, A union B equals set of all x such that x belongs to A or x belongs to B. The shaded portion represents the union of the sets A and B. U is the universal set. Next is intersection of two sets. For the sets A and B, the intersection A intersection B is the set of all elements belonging to both A and B. That is, A intersection B equals set of all x such that x belongs to A and x belongs to B. The shaded portion represents the intersection of the sets A and B. Next is complement. For the set A, the set A complement equals set of all x such that x is not an element of A is called the complement of A. The shaded portion represents the complement of the set A. Next, difference of sets or relative complement. For the sets A and B, the set A difference B equals set of all x such that x belongs to A and x is not an element of B is called the relative complement of B with respect to A. The shaded portion represents the complement of the set B relative to the set A. It is clear that A difference B equals A intersection B complement. Infinite sets are again of two types, namely countable sets and uncountable sets. The sets whose elements can completely be written in an order are countable. The set of natural numbers is clearly countable. The set of integers can be written in the order 0, 1, negative 1, 2, negative 2, 3, negative 3, etc. Infinite sets which are not countable are uncountable. A union of two countable sets is a countable set. Let A equals set A1, A2, A3, etc. and B equals set B1, B2, B3, etc. be two countable sets. Then A union B can be represented as set A1, B1, A2, B2, A3, B3, etc., which is a countable set. A countable union of countable sets is a countable set. Now, let A1, A2, A3, etc. be countably many countable sets. Then, their union will be a countable set. These sets can be assumed respectively as A1 equals set A11, A12, A13, etc. A2 equals set A21, A22, A23, etc. An equals set An1, An2, An3, etc. and so on. Now, union n ranging from 1 to infinity An equals set A11, A21, A12, A31, A22, etc. defines the order of elements and thus proves the countability of the union. It can be noted that the sum of indices of terms gradually increase. The principle of inclusion and exclusion. If hash x denotes the number of elements of a set X, then hash A union B equals hash A plus hash B minus hash A intersection B. Also for three sets A, B and C, hash A union B union C equals hash A plus hash B plus hash C minus hash A intersection B minus hash B intersection C minus hash C intersection A plus hash A intersection B intersection C. Example, let there be 40 students interested in football and 35 students interested in cricket in a class of strength 60. Let us find the number of students interested in both these games. Here, if we represent these two sets of students as A and B respectively, then hash A equals 40, hash B equals 35 and hash A union B equals 60. By the principle of inclusion and exclusion, hash A intersection B equals hash A plus hash B minus hash A union B equals 40 plus 35 minus 60 equals 15. Next is multi-sets. In set theory, a set A, B, 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 C, C is simply understood as the set A, B, C consisting of only 3 elements. But consider the case of making a list of the names of students in a class. It can happen that more than one student to have the same name. In that case, a repetition of elements is admissible. In other words, the elements need not be all distinct. Such a set in which the elements need not be all distinct is called a multi-set. The number of times an element appears in a multi-set is called the multiplicity of that element. For multi-sets, the union, intersection, difference, etc. will be multi-sets. Note that any set is a multi-set, but there are multi-sets which are not sets. If P and Q are multi-sets, then the multiplicity of an element in P union Q is the maximum of the multiplicities of that element in the sets P and Q. The multiplicity of an element in P intersection Q is the minimum of the multiplicities of that element in the sets P and Q. For two multisets P and Q, the multiset P difference Q is a set in which the multiplicity of an element is the difference of the multiplicities of the element in the sets P and Q if the difference is positive and 0 if the difference is 0 or negative. Example, let A equals set 1, 1, 2, 3, 3, 3 and B equals set 1, 2, 2, 3, 4, 4, 4, 4, then A union B equals set 1, 1, 2, 2, 3, 3, 3, 4, 4, 4, 4, A intersection B equals set 1, 2, 3 and A difference B equals set 1, 3, 3. Propositions. Any declarative statement is called a proposition. In other words, a statement for which the only possible truth values are either true or false is a proposition. Consider the following list of statements. Delhi is the capital city of Pakistan. The planets in the solar system are moving around the earth. 1 plus 3 equals 4. Root 2 is an irrational number. How bright is the light? Is the summer in Kerala really horrible? The leader of the class is very smart. The statements 1 to 4 are propositions. The first two of them return truth value false and the next two return truth value true. The last three are not propositions since one of them is an exclamation, the other is a question, and the truth value of the last may vary according to the person who evaluates it. A proposition that is always true is called a tautology, and a proposition that is always false is a contradiction. For two propositions P and Q, compound propositions like the conjunction P and Q, the disjunction P or Q, the conditional statement if P then Q, the biconditional P if and only if Q, and for any proposition P, the negation not P etc. can be formed. Usually, the truth value of a compound proposition corresponding to the truth values of the simple propositions contained in it, called atomic statements, are represented by truth tables. The most simple type of compound propositions are conjunction, disjunction, conditional, biconditional, negation, etc. To make things clear, truth tables of such propositions are given below. First is truth table for conjunction P and Q. The first column represents P, the second Q, and the last P and Q. If P true, Q true, P and Q is true. If P true, Q false, P and Q is false. If P false, Q true, P and Q is false. If P false, Q false, P and Q is false. Next is truth table for disjunction P or Q. If P true, Q true, P or Q is true. If P true, Q false, P or Q is true. If P false, Q true, P or Q is true. If P false, Q false, P or Q is false. Next is truth table for conditional if P then Q. If P true, Q true, if P then Q is true. If P true, Q false, if P then Q is false. If P false, Q true, if P then Q is true. If P false, Q false, if P then Q is true. Next is the table for biconditional P if and only if Q. If P true, Q true, P if and only if Q is true. P true, Q false, P if and only if Q is false. P false, Q true, P if and only if Q is false. If P false, Q false, P if and only if Q is true. If two compound propositions have the same truth values corresponding to the truth values of the simple propositions involved in them, then the compound propositions are said to be equivalent. The equivalence of propositions can be checked using truth tables. Mathematical induction. This is a method of proving a mathematical statement involving a natural number n. Usually, a statement or proposition involving n is denoted by P of n. The method of proof of a statement by mathematical induction runs through 3 steps. Step 1. Basis of induction. The statement is verified to be true for some particular number, usually n equals 1. Step 2. Inductive hypothesis. The statement is assumed to be true for some number n equals k. Step 3. Inductive step. The statement is verified to be true for n equals k plus 1. Example. The principle of mathematical induction is used to prove that the sum of the first n natural numbers is half into n plus 1. Take P of n as the statement 1 plus 2 plus etc. plus n equals half into n plus 1. Step 1. When n equals 1, the sum is 1 and half into n plus 1 also is 1. Thus, P of 1 is true. Step 2. Assume that P of n is true for some k, that is 1 plus 2 plus etc. plus k equals half into k plus 1. Step 3. When n equals k plus 1, 1 plus 2 plus etc. plus k plus 1 equals half into k plus 1 plus k plus 1 equals half into k plus 1 into k plus 2. Thus, p of k plus 1 also is true. By the method of mathematical induction, the proof is complete. Example: any integer composed of 3 raised to n identical digits is divisible by 3 raised to n. For example, 777 is divisible by 3, a number composed of 9 5s is divisible by 9, etc. Step 1. When n equals 1, any number with 3 identical digits has sum of its digits a multiple of 3. Step 2. Assume that any number with 3 raised to k identical digits is a multiple of 3 raised to k. Step 3. Consider a number x with 3 raised to k plus 1 identical digits. Then x equals y into z, where y is a number with 3 raised to k identical digits and z equals 10 raised to 2 into 3k plus 10 raised to 3k plus 1 equals a number 1 followed by 3k minus 1 zeros, again a 1 followed by 3k minus 1 zeros and again a 1. This number is clearly divisible by 3. Now, since y is divisible by 3 raised to k and z is divisible by 3, x is divisible by 3 raised to k plus 1. Thus, the statement is true.